Well, it's time for our daily lesson in accounting and bookkeeping. And this little thing, as Kim is called an ICE table, to help us keep track of things, especially in an equilibrium situation. Although some texts, some authors, some folks even use tables like this when talking about stoichiometry in general. But let's try a couple. And perhaps you've practiced with them already. If you have already, you could probably ignore this video, although it's good to see more examples. Can't have too many examples. Here's an equilibrium with the nitrogen gas, hydrogen gas to form ammonia. And let's see, we're not even told what the constant is. I think we're supposed to find out what is the value of the equilibrium constant. But they don't tell us exact equilibrium concentrations. They say we put 0.561 moles of N2, 0.672 moles of H2 into an empty 1 liter container, and we wait until it reaches equilibrium. The reaction proceeds forwards until the creation of 0.279 moles of NH3 ammonia is observed or made in the equilibrium. From that alone, we're supposed to find out what the equilibrium constant is, or the concentration constant. So luckily for us, it's in a 1 liter container. If it wasn't in a 1 liter container, I would just divide the moles by the liters to find molarity. Although you can use this table for just straight up moles, as we do in some situations, but eventually before you put it into the law of mass action or the equilibrium constant expression, you do have to change to molarity at some point. I went ahead and did it now. So if I start with 0.561 moles in a liter of nitrogen gas, 0.672 moles in a liter of hydrogen gas, and they didn't mention any of this in the beginning, so I'm going to assume that's a zero. If they don't mention it, there's probably none there. Although they do say that after this thing comes to an equilibrium, we have 0.279 moles in a liter. They didn't say anything about this and anything about this, but I'm predicting that I still will have some. This one and this one react to give this one, but as more of this forms, then that backwards reaction picks up as well to make more of this and more of this. So it's a complicated, seemingly complicated interplay of forwards and backwards, and it almost seems like there's no way to know, but actually there is a way to know. It goes like this. Initially I have these concentrations. How do they change? They change in a way going up or down so as to reach equilibrium concentrations. If these two are if all I have are these two gases as reactants and none of this, doesn't it make sense to say that these two will go forward to make some of this? In other words, from 0 to something. And that something in this question was actually given to us. So, interesting. How about I claim that I can figure out this number? 0 plus what number gives you 0.279? Well, duh, it's 0.279. 0 plus 0.279 gives me 0.279 in the end. So setting up this table correctly is the key, and thinking about what you're told and what you're asked. Well, if this one goes up by 0.279, does that mean that this one goes up or down? The answer is down. If these two are the reactants, they will go down to something less, but they won't go to 0 because of the equilibrium interplay. We go forwards and backwards and forwards and backwards, and the constant describes the amount that it'll have in the end. In a way, it's hidden, but anyways, this is going to go down. The question is, will it go down by the same 0.279 number? And you might think so. This goes up by 0.279, this goes down by 0.279. Yeah? No. There's a 2 here. There's a 1 here. Here's where the stoichiometry, the balanced equation, comes in. This will increase by 2 times more than this will decrease. One of these for every 2 of those. So this will go down by half of 0.279. What about this? This will go down as well. If this goes down, this has to go down. These both go down so as to consume some to create some of that. Will this go down by 0.279? Will it go down by half 0.279? No and no. The answer is 1/3. No, not 1/3. Well, let's see. This is a 3. That's a 2. Might be difficult or tricky to relate this to this. How about I relate this to this? How about this decreases 3 times more than this decreases? Excellent. Here's what I wrote. Yeah. this goes up by 0.279. 0.279 is close to 3 sig figs anyway. Half of that's 0.140. So this goes down by 0.140. If this goes down by 0.140, this goes down by 3 times that amount, because there's a 3 there. 3 times that, or 3 times that. Actually, I think I took 3 halves of this number to get this number. Yeah, that's what I did. Well, now that I have my accounting, bookkeeping filled in, I can go ahead and plug it in our old friend, the law of mass action, the equilibrium constant expression concentration version, where I have the NH3 concentration, molar concentration, in the upstairs squared, and the downstairs N2, and H2 cubed, and this goes here, and this goes here, and this goes here, and you plug and chug, 11.4. Interesting. 11.4. I'm not going to comment on that. It's larger than 1, but not that much larger than 1 on the scale of thousands or thousandths. Okay, let's try another one of those. Or, wow, you could pause the video. You could try this yourself. It works with pressures as well. Kp, what's the value of Kp if I start with 200 torr of this reactant, none of this reactant, 200 torr of this product? Well, that's confusing. If I have none of this and some of this and some of this, can I establish an equilibrium? Yes, some of this will go backwards to make some of this, to fill in that emptiness. Of course, in that process, Mother Nature will also create some of this, and we're told how much of this is created. 5 torr-ish. To go from 200 torr to 205 torr, that's what was told. You got to read this like 3 times and do 30 of them or 30,000 of them until you can become comfortable enough with the vocabulary and the way they might ask the question so as to be able to fill in a table like this lickety-split, fast, like a pro. So if this goes up from 200 to 205, this one goes up by, does it also go up by 5 torr? No, it goes up by 3 times that much. So how about 15 torr? So 0 plus 15 is 15 torr. This one goes down. If these two go up, if this goes up, this goes up, this goes up, this must go down, because this is being used to create some of that. That'll go down by, what'll it go down by? 5 torr? 15 torr? How about 2 times this number, which is 10 torr? And if that's the case, I think I said that correctly. The pressure constant is calculated the same way. Put this number in the numerator squared, put this in the bottom cubed because there's a 3 there, and put this in the denominator, and there's nothing new there. So the new thing is the ice table. Coming up with it, creating it, thinking about it, what's changing, what am I given, what am I asked, what goes up, what goes down, by how much does it go up and down. My last example, I'm not going to finish, but I'm going to start it. I'll finish it later. A new equilibrium equation, one of these and one of these are in an equilibrium with 2 of these. The constant's 220, quite a bit bigger than 1. So in the end, I might expect probably more HF. There are an exception I can think of, but whatever. 2 moles of H2 and 3 moles of F2, 2 moles of this and 3 moles of this, put into a 1 liter container, allowed to equilibrate. Here, you're given the constant, and I'm asked to find the equilibrium concentrations of one thing or another. Excuse me. It's in a 1 liter container, so I have 2 moles in a 1 liter, 3 moles in a 1 liter, none of this. So if I have none of this, isn't this going to go up to something? And if this is going to go up, then across the arrow, this will go down, this will go down. But I don't know exactly by how much. So you know what? All I'm given is a constant. This constant 220 somehow describes my ending proportions, my ending ratios, according to that law of mass action expression. But I don't quite know what this is and this is and this is. But if I'm smart, I can figure it out. If I have none of this, it's going to go up. And if I have some of this, these will go down. This will go down, this will go down, this will go up. I don't know by how much this will go up. I don't know by how much this will go down. So how about I call this one X? I'm choosing this one to be X on purpose because there's a 1 in front there. There's also a 1 in front there, so I could call either this one or this one X. I think this one's going to go down by X, and this one's going to go down by X. If both these go down by X, this one's going to go up by x? 2x. So how about I fill in my table something like this? Whoa, this looks like algebra. What'd you come up with an x for? 2 minus x, 2 goes down. 3 minus x, x goes, this concentration goes down. 0 plus 2x, because there's a 2 there. Now I'm ready to fill this into my law of mass action, just like I've always been writing. Kc is my HF in the top is squared. H2 and F2 both in... Oh, that's a typo. Except I wrote this out. That should be F2. What do you know? They're in the same family. It'll go. It'll work. I'm kidding. But put an F there. When you write this in your own notes, right? Put an F there. F2. Yeah, the constant's 220. So, gosh, I don't know this. I don't know this. Oh, my word. First, outer, inner, last FOIL. Remember how to multiply two x terms together? This one times this one. 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 Did I get all of it? I lost track. Anyway, that's what you get. And lo and behold, you solve it, or you try to solve it, and you come up with what's called a quadratic equation. Yay, another video. That's enough for now, though, because I haven't solved this. I don't know. I'm going to have to scratch my head for a second. I'm just kidding. I know how to solve it. I'm going to have to scratch my head and say, how do I solve for x? And when I do so, what does it mean? Does it have physical meaning in this, in my attempt to solve this, the equilibrium quantities? The answer is yes, and I'll tell you later. See you in class. Thanks for watching.